Good evening, ladies and gentlemen. I think it's exactly 5 p.m. now. So I am Udeni Navagamu, the chair of this History and Heritage Forum of the ISL. Before starting the presentation, I would like to welcome you all for this inaugural session of this History and Forum. So this is the first lecture organized by the History and Heritage Forum of the ISL. Before introducing the presenter today, I would like to acknowledge the person who was the link in inviting the presenter. He is the president-elect, Dr. Kamal Laksiri. He had worked with our presenter for several years back. And because of that connection, we were able to invite the speaker today. So Gil Jolef is a senior lecturer at the University of Exeter in archaeology. Gil Jolef is an archaeometallurgist specializing in early ferrous technology. That means the technology of iron. Gil combines field investigation with laboratory-based analysis to examine early technological development within its social and environmental context. Her main research areas are in Sri Lanka and India, where she is engaged in two research projects, monsoon steel and pioneering metallurgy. Further afield, Gil's research encompasses early iron production across South and Southeast Asia. In England, Gil has directed the Exmoor iron project for a number of years, which is examining early iron production on Exmoor. At Exeter, Gil teaches the artifacts module, archaeometallurgy, experimental archaeology, and the archaeology of South Asia and the Indian Ocean. Yeah, without taking much time from Gil's due time, right? So I would like to invite Dr. Gil Jolef to start the proceedings. Thank you very much. Gil, over to you.
Thank you very much for the invitation. It's fantastic to be able to talk to you all today, and I'm just looking at my screen and seeing that we have well over 60 participants. That's a lovely audience. We had a go at the technology earlier, and in a moment I will share my screen with you. I've got quite a lot of slides today. I know that Sri Lanka at the moment is going through a very difficult situation, and my thoughts are very often with you. And I hope that today's talk is going to be something of a distraction, if only a temporary one, but I hope also a positive one. Shall I share the screen now? First of all, can anybody put into the chat if they have any problems hearing or seeing the screen or any technical issues, because I'm hoping it will all run smoothly.
It's very clear, Gil, right? So we can start.
Thanks. The presentation. Thanks very much. Okay, well, I will share the screen and I will use that one. And then ask you if you can see all of that. It might take a moment for it to come through.
Yes, it's fine. It's perfect.
Lovely. Okay. Okay. Well, I hope I don't go on for too long. If I'm overrunning a lot, just let me know. I've got quite a few slides to get through. I put in the title of the presentation today. Oh, I want to go back. What's that doing? Why is that going? Why can I not go back? Okay, I put in, let's just hope that that doesn't do that again. I put in the title, The Unexpected Story of Iron and Steel Making in Sri Lanka. And I put in unexpected because that's very often the reaction that I get when I talk to people beyond Sri Lanka about this story. And I think it's important for us to think about why it's so unexpected. But anyway, let's start. I want to start by thinking about a bigger picture and perhaps trying to contextualize what Sri Lanka has to offer in this whole field of iron and steel development. And as your engineers, I'll start with something that I'm sure many of you have in your minds and read about a lot, and that is the whole concept today of super materials, and what we can do with them and how they can help and enhance society. But let's think about now, why is I'm not getting my PowerPoint to move on. Why is that? Oh, I think I know. There we go. Sorry. Probably the original super material was in fact steel, and we're talking about a material which was first invented or emerged over 3,000 years ago. And this is an amazing alloy of iron and carbon, and the fact that you need less than 2% of carbon in iron to create this incredible alloy. But getting 2% of carbon into alloy is not a simple task to persuade it to go. So there's a lot of technology involved. So what can steel do for us? What it gives us is the chance of making tools that will cut, that take edges. It allows us to make domestic tools, agricultural tools. It allows us to cut very hard materials and carve them. And we know from Sri Lanka the amount of carved granite. You can't carve the granite in Anuradhapura without steel tools. Allow you to make tools. It gives a chance of making blades and edges that are hard, that are strong, and that are flexible. And once you can do that, you can start making weapons. And there's nothing that drives technology like the opportunity to make weapons. It's a sorry thing to say, but it is the reality. So this is the material we're dealing with. So I'm going to just introduce a little bit of technology. You're engineers, so we ought to be able to deal with this. Making iron and steel is not easy. It takes a great deal of technological know-how, experience, and what I want to do here is just to look at some of the ways that we can make iron and make steel. If you look at the screen, the bottom of the screen, we have can I get my cursor there? This bar along the bottom. It's just a very simple way of describing different types of steel and the amount of carbon you need in the iron to create the steel. So on the left-hand side of the screen, you have wrought iron, which has almost no carbon in it. It's quite soft. And as you get carbon into this, you've got perhaps as little as 0.1% carbon, you begin to make a steel. By the time you get up to 0.8% carbon, you've got a very high quality eutectoid steel. You've gone through the mild steels to eutectoid steels. Once you get over 0.8% carbon, you have high carbon steels. And these are the steels that make the blades, the tools. But if you push the carbon over 2%, you then move into the cast irons. And the cast irons we know are very hard, but they're brittle. And they really don't have anything like the usage of steel. So that's this very short alloy trajectory. If we look at the top of the screen then, these are the two main routes that we recognize as ways of making iron and making steel. On the left-hand side, you have what we call the direct process, where you take iron ore, you smelt it in what we call a bloomery furnace. It's not a very good term. I don't like using it, but it's what we might call a traditional furnace, and it makes a soft wrought iron. And it aligns with that scale at the bottom where we have that soft wrought iron moving into low carbon steels. On the right-hand side of the screen, we have the indirect process. And that's the process which dominates in today's world and is the blast furnace technology, where you take the same iron ore, but you smelt it to a cast iron, which is hard and brittle. So neither of these processes are making steel. To make steel, you have to do something further with your iron to refine it to produce your steel. And it's the, right, my mouse is working on one screen and my keyboard on another, so I need to use the keyboard. So it's this central area where is that sort of holy grail of iron metallurgy, where we're making these steels and how we get to that point. So on either side of that, the direct process is perhaps what we would call the pre-industrial, the craft, the small-scale smelting, where me as an archaeometallurgist does most of their work. And on the right-hand side, the blast furnace technology is what we would call industrial, it's advanced, it's developed, it's large scale, and in many ways it's dominated from a Western technological perspective. Okay, I don't know, somebody's got a microphone on, I think, yeah? So this is the indirect process. If anybody says to any of us here in the audience, iron making iron, making steel, these are the sorts of images that come into our head. Blast furnaces, big industrial processes, very advanced, you know? And on top of that, if we think about taking the material from a blast furnace and beginning to make these steels, and particularly trying to make the really high quality steels, we have in the Industrial Revolution the development of specialist steels or crucible steels in places like Sheffield and elsewhere on the continent. We have famous steel makers. The Huntsman of Huntsman Steel developed a crucible process for making high carbon steels. Faraday, Mushet, Wilkinson, all big important names in the development of steel technology in the 19th century, and big players in the history of the Industrial Revolution. But what is really interesting, and it's rarely talked about, is in fact these people were taking their inspiration from high carbon steels that were coming from India, ingots of high carbon steels. And we tend to sideline the fact that so much of the inspiration for the Industrial Revolution in the West, in Britain and in Europe, was actually being driven by technological developments in Asia. So making iron and making steel takes an enormous amount of technological knowledge and experience. It also requires a high level of social investment and organization and planning. And because of that large scale of investment in the fuel, in the apparatus and the infrastructure, the months of planning before you even get to smelt iron, you need to succeed. So there's an economic imperative to succeed. You can't play with this. It has to give a return. And it's in many ways why the whole Industrial Revolution dominates our thinking. And when we think about making iron, we think of these big players who have the political ability to invest in this stuff. So we think about Britain, we think about Europe in the 19th century. More recently, in the 20th century, late 20th century, we think of America, the USA, China, and also India. We don't tend to think about places like Sri Lanka, which is why all of this is unexpected. But we do have some indications, some hints that there is more to understand about the technology of making iron and steel in Asia. And we also begin to understand there's a greater complexity to this rather simplified model we were using. We know that the Industrial Revolution was taking the ideas of crucible steels from India, and we also now know Sri Lanka. We also now begin to appreciate that there are ways of smelting directly from iron ore to steel, and that we see some of that in Japan and now in Sri Lanka and occasionally in Africa. So it is a more complicated story. So to think about some of those hints about the technological history, and to come a little bit more locally in Sri Lanka, we can look at a treatise written in Arabic. This is a translation and an interpretation of a treatise written in the 9th century by a very revered writer called Al-Kindi, who wrote a treatise on the kinds of swords and iron. And in it, there are at least multiple times he mentions the quality of Serendipity or Sri Lankan steel. And so for a very long time, scholars thought that this was referring to steel that was made in India and was transshipped through Sri Lanka. Nobody really could quite believe that Sri Lanka was part of this production technology for steel. We also, if we look at foreign visitors to Sri Lanka during colonial periods and earlier, we see mentions about the quality of the iron and steel. And we've got quotations here from 1608. These Sinhalese are very apt at manufactures and have a very cunning and delicate hand for iron and steel. They make all sorts of arms, which are the best and most valued in the Indies. So this connection between making iron, making steel, and making arms is very important. Robert Knox in 1681 says manufactures iron and steel, iron tools for smiths and carpenters, carved work, making steel and good guns. So again, the same connection. And then later we have Emerson Tennant, who says the quality of iron ore found in Ceylon is singularly fine. The iron wrought from it requires no puddling, and converted to steel, it cuts like a diamond. So we have these really important hints that there is a tradition of making iron and steel in Sri Lanka. Perhaps the most interesting and exciting account is that by Ananda Kumar Swami. And I'm sure quite a few of you know this. In medieval Sinhalese art, at the turn of the 20th century, Ananda Kumar Swami, along with his wife Ethel, his English wife, witnessed iron being smelted and steel, crucible steel being made at two villages in the Balangoda district, Hatharabage and Mawalgaha. And not only does he witness this, he gives in medieval Sinhalese art a full description, a full account of the process with plans of the furnace, with dimensions, and particularly photographs. So this account is probably one of the most valuable ethnographic or anthropological accounts of iron making and crucible steel making, and the only one for crucible steel making from anywhere in the world. So these are really valuable, and these are what provided me with a starting point for my research. So we've gone from a big global picture and thinking about the scale of the industrial scale of making iron and steel, to something more local and more regional, and thinking about the fact that making iron and steel requires such an enormous investment, we expect it to be within the hands of the really big political regions of the world and the rich. Okay, we're going to move on to talk much more about the work here in Sri Lanka. And we go right back to the start of my research and the Samanalaveva archaeological project. Well, that's, we all know what that means, but it's a bit of a mouthful if you're looking for someone to fund the work. So the title Samanalaveva Archaeological Project soon turned into Monsoon Steel, which is much more accessible for anybody beyond Sri Lanka. So to give you an idea of what I want to cover in the next batch of slides, the research history at Samanalaveva began in the late 1980s and really began by trying to search out the places on the ground where Ananda Kumar Swami saw iron and steel being made and wrote his accounts about. And that was part and parcel of a much bigger survey of the area that was being impacted by the Samanalaveva hydroelectric scheme, which was a full archaeological survey. The results of that then led on to an excavation project in the early 1990s to excavate one of the sites that we had identified. And that in turn led on in the mid-90s to the experimental reconstruction of some of the technology that came out of that work. And leading on from that, we conducted more experiments from 2007 and again later, and developed the research agenda and asked more questions of this material. So we're going to go through that as efficiently as we can. You all know this place, and you all know on the map roughly where Samanalaveva is, the Balangoda district, on the southern side of the Central Highlands. I've also noted in Sigiriya, because we'll talk about that briefly. The important thing about the Samanalaveva area is that from a climatic point of view, it is on between the wet zone and the intermediate zone, which gives it a distinctive climate, especially given its type of topography in relation to the Central Highlands. It has its climate is dominated by the southwest monsoon, but because of its position, the monsoon, which we know is a wind system, has dropped its rain in the wet zone, and by the time it reaches Samanalaveva, it's blowing as a dry wind across this region. So we'll come back to that. Just another view of the area where we've been working. This is looking from the south, from the lowlands up to the highlands in the far distance. The escarpment in the mid distance is the Kaltoti escarpment, and Samanalaveva lies on the plateau that's above that escarpment. So we're sandwiched between Central Highlands and the lowlands that reach down to the coast. But that plateau, on that plateau, we have a very, it's not a plateau, it's a very varied terrain, hilly terrain. We have cultivated valleys where we have rice cultivation, we have small village settlements, but the landscape is actually dominated by jungle and windswept hills. So it's certainly, when we started the work back in the 1980s, it was not densely populated. And it's the hilly terrain that was where most of our work was concentrated. So just to give you a short summary of what came out of our initial field survey, we did a survey that took us 3 months with an additional 1 month survey extension, covered an area of a core area of 58 square kilometers, and then we extended that by another 20 square kilometers. Within that area, we identified and recorded 253 sites. And these are all sites because this was a survey that was conducted with the Archaeological Survey Department. And worked with a fantastic team there through the whole of this project. So those sites were divided between prehistoric sites. We had something close to 80 small prehistoric campsites on the hilltops, would just be a few stone tools. We had a number of historic sites, which were not to do with metallurgy. And these were sites such as settlements where we found older pottery or the site of a bridge or the remains of a temple, although there were very few of them. But by far the largest group of sites were the metallurgical sites, sites associated with the production of iron or steel and steel. And of those 140 sites, they divided into 3 basic groups. The first group were the sites that were located in the valley bottoms, in the villages, and these were sites that were associated with the technology described by Kumar Swami in medieval Sinhalese art and photographed by him. We have 42 of these sites. And then we had a group of sites which we had no indication of before we started the survey. And this is by far the largest group of sites and continues to grow. The count is now over 88 sites, and I'm sure we could find more. And these are what we call the west-facing iron smelting sites, because they were situated on the tops of hills in windy positions, and we found material on the west side of those hills. Excuse me. And then we had a number of other sites that were associated with metallurgy. That might be ore deposits, blacksmith sites, etc. And just for the engineers or for anybody, what's interesting to know is that only 25% of the sites that we identified and recorded are actually now lost to the flooding of the reservoir. 75% of what we recorded are still visible and they're not within the reservoir. So it's not as if we've lost this material, far from it, especially these really important west-facing sites because they're up on the hilltops. So how am I doing for time? Not too badly. So let's look at what we found during our field survey. I just wanted to, no, you're all still with me. Let's have a look at just a couple of points that came out of our field survey, focusing particularly on the west-facing sites. So what we were finding was that we had waste slag, the rubbish from smelting, which is simply left on the site, is dumped on the western slopes of these hilltops, not on the summits, but on the western side. So everything was pointing towards and facing towards the west. What we also found was this slag waste is a very distinctive morphology. One of the things that people like me do when they study archaeometallurgy is to look at this waste and see what the waste tells us about the process. So the shape of this waste and the shapes that it takes is very useful, important, valuable research material. So here we have some very unusual shapes of slag. Here's an intact piece which is over 1 meter long, which is exceptional. And it's a long linear shape. And in this one, I don't know how clear it is, I hope it's visible to you. We have 4 clay pipes that are called in metallurgy Twiers. They are the air pipes into a furnace. Here we've got these Twiers that have been telescoped together and used within the furnace, and they're all clogged up with slag. But they've created a barrier within the furnace, and it was a very distinctive shape that we saw over and over and over again on all of these 80 plus sites that we identified. We had several other distinctive features on these sites, but these are the ones I wanted to pick out for you. Well, what's important about those slag shapes is that they do not conform with anything that we would conventionally see from traditional Western furnaces, the sort of thing that we would normally expect to find. And here I just put in a couple of images of an experimental furnace here, right locally here in Devon. It's a small shaft furnace based on an Iron Age furnace. You can see it's like a chimney. If you look down the chimney, you can see this circular plan combustion zone within the furnace. This is whether it's a blast furnace or an Iron Age furnace. This is the conventional dominant furnace model. Our material from the west-facing sites does not come from anything that looks like this. So, moving on, the evidence that we had from the field survey was sufficient for us to have funding to carry on and excavate one of these west-facing sites. And the site we chose is very close to the dam, the Salmonella Veva Dam itself. We are within see the dam in the background. It's still under construction. Our excavation site is actually at the upper elevation of the reservoir, and all of you will appreciate the fact when I say that actually our site has never gone underwater. You will know what I'm talking about when you think of the Salmonella Veva Dam. One of these days, perhaps, we could organize a boat trip to go and look at this site, because it will be fantastic to be able to go there.
Please excuse me, someone has unmuted.
Yeah?
Yeah, that's fine, Gil. Right, so we can continue.
Sorry, carry on?
Yes, we can continue. Yes, please.
Right. Okay. We'll come back to he has a question. Fine. Okay, so this is the site that we excavated over a period of, now I've gone and lost this again. Let me come. Right, sorry. This is the site that we excavated over a period of about 6 months. You can see what you're looking at here is essentially the slag heap. All of the slag, the west is to the right-hand side of the screen. You can see where they're actually digging in the foreground. The soil is very black. That's from the charcoal and the residues coming out of the furnaces. The bigger lumps of material are lumps of slag. And what you can see where I put my cursor is you've got structures emerging from this slag heap. You have one here, you have two here, there's another one here. This group of people are digging one here, there's another one here, another one back here, another one back here. So these are furnaces emerging out of the slag. So these are the structures where the iron was being made. What's important is that we have a series of radiocarbon dates from this site, and they date the activity on this site to between the 7th and the 11th centuries. Interestingly, coinciding with the date of Al-Kindi's treatise on Islamic treaty on swords and iron, where he discusses serendipity steel. So these dates coincide. On this site, we excavated something like 41 furnaces, separate furnaces, and we only excavated less than 20% of this site. So there's an enormous amount of production and industry here. Okay, so what do these furnaces look like? This is what the excavated structures look like. They are constructed of clay. They are these rather elongated C-shaped structures. They're terraced into the hill, and they're never more than about ½ a meter high. And although they look as if they are broken, which they are, we know this because we have the rims of these furnaces. So we know that they're very low. This clay wall is terminated at either end with an upright stone. And the other thing that we consistently see is that the maximum heat damage to the clay occurs at either end of this wall, where it comes westwards and terminates with the upright stone. So we have this set of characteristics that repeated over and over again for these furnaces. And here's another one that of the excavated furnaces, and in this case we can see evidence for a wall to the west that would create a front across that C shape, but that wall is dismantled and it's collapsed, and we see in that the lumps of clay from the wall. We see those telescope Twiers that we were seeing during the field survey, and we also see sheets of molten slag that are intact, that have flowed in a molten state out of the furnace. There's a very dynamic image of the working of this furnace. There is the back wall of the furnace, that C-shaped, and here are the two upright stones. So this is a very active, and the fact that you've got molten slag that's able to flow 2 meters away from a furnace into the face of these very high velocity winds suggests that this is working at very high temperatures. Okay, so moving on from the excavation and the survey, the evidence that came from the survey and the excavation was strong, convincing, told a very good coherent story. It demonstrated a widespread industry across this region with these multiple sites. All of these sites are based on this very unusual linear shaped furnace that was using the dry southwest monsoon winds. That was all very convincing from an archaeological point of view. But the problem that we encountered was, or that I encountered, was when I presented that data to international community of archaeometallurgists, I was met with enormous skepticism. They were simply not prepared to believe this evidence, because they said that no iron smelting furnace has ever been demonstrated to be able to be operated using the wind. The furnace is too long, it's too low, and it's in Sri Lanka, and nobody would expect that. So really, on the basis of that, we concluded that the only way that we could take the research further was to actually reconstruct a furnace during the monsoon to see what actually happened, and if it could reach the temperatures that we needed it to reach to be able to smelt iron, and how it functioned, which is what we set out to do initially in 1994 and then again in 2007. And so the next set of slides come from the various different experimental smelts that we've undertaken, and they're just to sort of give you an overview of that process. It also gives you a bit of an idea of the amount of social investment and planning that has to go in before you even get to the point of being able to smelt iron, or at least attempt to smelt it. I need to say, I had never smelted iron before doing this, and I'd never actually even seen an iron smelting furnace in operation. So I was definitely working in the dark, but working off the archaeological evidence. We were simply trying to recreate the archaeological evidence to see what happened. So to start with, we needed a lot of fuel. Our local blacksmith friends made over a ton of charcoal fuel for us from species we knew were used in the archaeological record. We collected iron ore from local sources. They're all surface deposits. It's a really good lateritic iron oxide, mixed iron oxide, which is very good for smelting in this sense, because it has a good iron content, over 60% iron content, but plenty of other minerals which help in creating the slag and create and helping to convert the iron ore, the iron oxide, to iron metal. So it's a very smeltable ore, and we find this ore all the way across the southern half of Sri Lanka, and it's not something that there has to be deep mine for, because it's a weathering product on the hilltops. We roasted it. That means we just heated it in an open fire to further oxidize it and to drive off water vapor. And the two images on the left show it before, or rather during roasting, and then after roasting, and you can see it's changed color quite dramatically. The other thing which is important and tends to get forgotten is the clay used to build these furnaces. These furnaces have to operate well over 1,000 degrees centigrade. This clay has to resist those temperatures. It has to remain standing. So the container for iron smelting is extremely important. And with the help of our local villagers at Samanullaveva, we put together a mixture, a very complicated mixture of paddy field clay, termite hill clay, river sand, straw, rice husk, which was very, very carefully mixed and matured to build the furnaces. So we then built our furnaces. And all of this construction is based on archaeological evidence, apart from the wooden poles that we put in here, because we struggled to get our wet clay wall to stand upright. So we used poles just to help us to keep it stable, and they burnt out during the smelting. But you can see we have a line of tuyeres here. A local potter made us these pre-fired tuyeres, and the clay that we made is used to construct the furnace. So we're on a known site at a known furnace location. So this is the furnace after it's been built, filling it with charcoal and getting it lit and running. And this is what it looks like reconstructed, and we're starting to heat it up. You can get an idea of the wind by looking at people's hair and shirts and the trees in the background and the smoke in the background. The wind here is not only high velocity, that means it will blow during the monsoon, it will blow anything from 35 to 75 kilometers an hour. But what's also very important, it's almost monodirectional. So it's coming directly from the west. So locating and orientating your furnace is a very important part of the design of this structure. So this is what it looks like when we put the first iron ore in the top, on top of the burning charcoal. And that is replenished all the way through the smelt. So we were using anything up to 100 kilos, no, much more, 200 kilos of charcoal per smelt and 100 kilos of iron ore. So we keep replenishing that over 6 to 8 hours. The thing to note here amongst the engineers and the scientists is the scorching on the top of this front wall. There's very clear scorching, which you don't see to the same extent on the back wall. We'll see more of that as we go through. So this is what it looks like when it's really beginning to get going. And you can see by looking down at the Twiers that we've got very good high temperatures. We're getting into yellow heat, even white heat. And you can see in the short distance at the top of the furnace, we've got quite a steep temperature gradient between the temperature inside the furnace and the temperature of the burning charcoal on the top. If we look down from the top, we can also see that we've got the highest temperatures actually focused and concentrated behind the front wall. And again, you can see that black line along the top of the scorching along the top of the front wall. Again, the same thing, but what we're beginning to see now is we can see the flow of air and the flames that are actually coming up the inside of the front wall. Charcoal is burning more aggressively at the front wall, so it's tipping down here. The flame is coming up and the flame is curling over the top of the front wall. And if you imagine into the face of this very powerful wind, so into the face of a wind that may be blowing at 60 or 70 kilometers an hour. So you can't easily see inside the furnace. You can look down the Twiers, but you don't quite know what's going on until you see that first run of slag. This is the molten waste. It's a silicate. It melts at 1100 degrees centigrade. And once you see that, you know that the right sorts of reactions are taking place inside the furnace. On a number of the smelts, we are able to use pyrometers to record temperatures we are reaching. And right in the combustion zones, we are reaching some phenomenal temperatures, over 1400 degrees centigrade. And in one case, we went over 1500 degrees centigrade. So this, without having to pump a bellows or do anything, this furnace of its own accord will run at very high temperatures. This is how that structure looks well into the smelt. You can see we've had a lot of slag coming out of the bottom. The wooden poles that we put in to help front walls to stand up have all been burnt out. The ends, the corners of the furnace are burning down quite heavily. All of the smelts we've done, or almost all of them, went into the night. And the reason for that was it enabled us to see the flame and the gases on the top of the furnace more clearly. And also is a very dramatic experience. What it allowed us to see, this is looking down at the furnace with the wind coming from the west. was the way in which the airflow within the furnace would come up the front wall, the inside of the front wall, and then curve over the top of the front wall into the face of the wind, and then be driven back by the wind. The same again on this slide, which was from our first experiment. The wind is coming from the west, and yet the flame is flowing in a completely different direction, perpendicular to the wind, which tells us that the top of the furnace is within some sort of protective bubble. It is not being impacted by the wind that's blowing from the west. I'm not explaining that carefully. We'll see some more of that in a moment. So we get to the end of the smelt, 6 or 8 hours into it. We decide that we need to bring the smelt to an end. We do that by pulling down the front wall. And we did this because that's what the archaeological records seem to be telling us. It's probably the most dangerous thing you can do. It would never be allowed in this country. Health and safety would have me in court for doing this. But that seemed to be what the archaeology was telling us. It's very, very hot. You can only do it at a great distance with a 6-foot wooden pole. It takes a lot of effort. And this is, the sort of mess that gets made. And this is our furnace after, or soon after, the smelt is completed. And what's really exciting about this is that we see this line of Twiers here. The front wall has all collapsed. We see the damage in the corner of the furnace. We see the relative lack of burning on the back wall of the furnace. So this looks very like our archaeological furnaces. And that's one of the most important aspects of these experimental reconstructions, is the way in which it mirrored the archaeological evidence. So it verified our archaeological evidence. Oh, I'm still got plenty of slides to go through. Are we all okay for time? Anybody?
Yes, please continue. It's an interesting presentation. Please continue.
Okay, thanks. So just to look at that idea again, that at the bottom of the screen is the image I already showed of the archaeological furnace that looked like the front wall had collapsed and there was slag all over the place. And on the top of the screen is our furnace after we'd finished smelting. So, we were doing, not only was the furnace doing similar things, we were taking similar actions as well. Okay, so the big question is, what did we make in our furnace? And you can see here we're breaking up the slag at the bottom of the furnace, and out of that mess we retrieved several lumps of iron, what we might call metal blooms, iron blooms. Not very much. I would certainly not make it as a iron making magnet in the commercial world, but we did make iron, which we took to the local blacksmith, who at first was very skeptical that it contained metal, but we persuaded him, and he forged it very successfully into a small bar within a matter of less than 20 minutes. So what he had created, or what he had smithed from our bloom, was in fact low carbon bloomery iron, just the sort of material that we were seeing in that diagram in the sort of pre-industrial traditional process. And here's a microstructure of that metal, very little carbon in it, and it's relatively soft. It's the sort of stuff that we would find coming from a process at this side of our route to steel, from the bloomery pre-industrial side. However, we then went back and looked again at all of the stuff that had come from our furnace, and we found that actually half of the metal that we've made was still stuck to the slag at the bottom of the furnace. Clearly a shortcoming in our technique in that we weren't able to separate this metal, but this metal, when we analyze it, is high carbon steel, and it's been molten. And you can see that from the shape that it's forming here. It's been liquid, and it gives us a very, very different microstructure. So we were, or our furnace, not me, the furnace was capable of smelting direct to high carbon steel. So rather than being stuck, or rather than being in the bloomery side of this diagram, we're now actually covering much, much more. We're directly smelting the steel. We have soft bloomery iron. So quite a different technology. Okay. So there was great excitement about the results of our experiments. All of those archaeometallurgists who had been skeptical, all very, very generously changed their minds and accepted all of these results. And Sri Lanka was put on the international stage in terms of making iron. What also, as a sort of addition to that, was again, it reinforced the overlap between this west-facing technology and all of these sites at Salmonella, all capable of producing high carbon steel, and the overlap with this description of serendipity steel being used in the Islamic world at exactly the same time for sword making. So it's possible that we could actually, this steel being used for Islamic swords was not coming from crucible steel, which is another technological story which we can save for another lecture, but possibly coming directly from these furnaces. There's still a great deal of research to do with this, but it's important. But what came from all of the excitement about those experiments was a lot of discussion about this unique technology in Sri Lanka, and that was the big fanfare. But I was never comfortable with that. And in the back of my mind, I kept thinking, is it unique? You can't use the word unique. Technology is rarely unique. It's part of a process of innovation, of adaptation. If you call something unique, it's a one-off. It doesn't go anywhere. It hasn't come from anywhere. It stands alone. And I can't believe that of this technology. So I had these questions in my mind. Where does this technology come from? Where did it go? What influenced it, and what did it influence? So a lot of questions still to answer. So to try and answer some of that, having reconstructed the technology, the next stage of the research process really is to deconstruct the technology again, to really pull it apart and examine what are the components that make this technology function in the way it does, and try and answer some of these questions. So obviously, let's go through that deconstruction process. Obviously, the most prominent and obvious feature of this technology is the wind power. And we've learned through experimentation just how tightly engineered these furnaces are to make the best use of these monsoon winds. And we know that it's not about the wind blowing down those tuyeres and into the furnaces. It's about pushing the wind over the top of the furnace and creating the vacuum within the furnace that then pulls the air through it. Which is why that black line at the top of the front wall, this is a section through our furnace, why that black line at the top of the front wall is so prominent and so important, because it's that point at which the airflow divides and rises over the furnace and creates this internal recirculation zone. So this was our first interpretation of what we seem to be seeing in our experiments. Since then, we've done some work using computational fluid dynamics at Exeter and refined our interpretation somewhat. More important than that, and really exciting, and I hope some of our authors are here in the audience, I now see that there are 2 new papers using, again, computational fluid dynamics to further analyze these furnaces and understand them. And I think this is a fantastic research road to go down. There is so much that will come from this. I'm really pleased to see that. But beyond the wind power, there's more to this technology than just the wind power. We have this slag morphology, the slag debris, and what that is telling us. And we, having identified these structures in our field survey, further work, we can see these shapes that we're getting from our slags are very distinctive and very particular, and help us reconstruct how this technology and how these furnaces were constructed and how they operate. That leads us to think about the actual design of the furnace. This sheet, well, we can call it a D-shaped furnace because we put the front wall in front of it. This is our reconstruction drawing after we've done our experiments, and you can see how we consider the furnace's design. Its orientation relative to the west wind is also important, but it would take me too long to discuss that in detail. What's really important is this design is radically different to the dominant Western model of a shaft furnace, the circular plan of a shaft furnace. This is totally different. And that shaft furnace could be an iron age furnace, it could be a blast furnace, but that is the Western model or the dominant model. So we looked at that in more detail and thought, what is the impact of that different geometry? What does that, what can we learn from that? And looking down our traditional Western circular plan furnace, we can think about this as the effective unit area of the furnace. This is what you need to create for a furnace to operate. You need to be able to create the right level of combustion with a given amount of air. Once you do that, you can construct your furnace around it, your apparatus. So this is perhaps our starting point. Oh, I should have gone back. However, if you've got that shaft furnace and it's successful, and you say, okay, I want to now make this bigger, I want to develop it, what do? You make your furnace larger, but you immediately hit a problem because you have to blow in more air, and most effective unit areas are optimized for the amount of air you're able to blow into it. So if you want to double the diameter of your furnace, you've got to blow in at least 4 times more air, or you've got to increase the flow rate by 4 times. A better way to approach that would be to increase the number of effective unit areas. So now you've doubled the size of your furnace, the diameter of your furnace, you've added another unit area. More effective would be to put 3 in there. Yeah. So let's follow that idea through a little further, and I'm sure the engineers amongst you are going to come back and query some of this, but it makes sense to me. So you want to scale up and develop your shaft furnace. So what you do is you add in additional effective unit areas. You have more points of airflow into your furnace, but as you scale up, you start to create this dead area in the center of the furnace. So just by increasing by 3 diameters, or greater, you start to put your furnace into a very difficult situation, because you now have a zone of combustion around an inactive column of fuel. And this is exactly what happened with the blast furnace. And this is a blast furnace design. You have a real problem with this geometry. If, however, you take a different route, and instead of using a circular model, you use a linear model, and you start to line up your effective unit areas, you're still blowing in the same amount, but you can now double or quadruple your furnace. And as long as your distance between the front and the back of the furnace remains the same, you don't increase your dead area. So, I don't know, for me, that makes a lot of sense. I can see why a linear furnace has a great deal more flexibility than a circular furnace. Okay, so that's deconstructing. So the next set of questions we had were, where did this technology come from and what did it influence? And that whole question of how unique it is. And still in the back of my mind is, it's not unique. Is it unique? Can we call it unique? What we have at Salmonella in our archaeological record is one much, much earlier furnace. We have one furnace that looks different and is dated to the 4th century BC. So almost 1500 years earlier than our wind-powered furnaces. But if we look closely at this furnace, we can see similarities. We have a structure, albeit somewhat smaller, where we have stones connecting a curved furnace wall, a clay wall. This stone has been robbed out, with a straight wall across the front. We know from the debris that came from this furnace, it had multiple tuyeres. And if we simplify this furnace into this schematic footprint, this is what we're looking at. 2 stones, a back wall, and a straight front wall. Now we're going to look at the furnaces at Sigiriya, which were excavated by Swedish archaeometallurgists with another team from the CCF. And you can see some similarities here. A better image is this. These are taller, bigger furnaces, but again, we look at the excavation plan, we have upright stones connecting a clay wall with some sort of straight barrier at the front, which is dismantled. If we translate that into a footprint, this is what we're looking at. It looks beginning to look familiar. Now, if we look back at our furnace we've looked at several times, which is this particular furnace is in our 2nd phase at Salmonella, and it's dated between the 9th and the 11th. And if we think of this in terms of 2 measurements, the distance between the upright stones, and then the distance between that front wall line and the back wall. And we think about those 2 dimensions and start with our earliest furnace at Salmonella in the 4th century BC. We have the distance between the 2 stones at 0.5 meter and the distance from the front to the back wall at just over 0.5 meter. So it's more or less equiaxed. Look at Sigiriya, which is a little later in time. We have extended the front wall, but we've reduced the distance between the front and the back. Then if we look at the first phase at Salmonella, we've even further extended the front wall and again reduced the distance from the front to the back. You can see what's happening here. So when we get to the 2nd phase at Salmonella in the 9th to 11th centuries, we've taken our furnace length over 2 meters, but we haven't changed the distance from the front to the back. So we have here, in archaeological terms, I hope in engineering terms, a very convincing evolutionary series where we've gone from an equiax furnace to a linear furnace. That convinces me to the extent that I can't remember when I wrote this, 2008, 9. I wrote a paper in World Archaeology called Technology and Evolution, where I presented this evidence in a sense rather like an evolutionary tree, and showing this Sri Lankan series using the concept of this linear furnace getting longer and longer, and distinct from the branch of this tree which uses the circular plan furnace. You can see here I've added in Cambodia, Japan, and Burma. So the story doesn't end with Sri Lanka. So our next questions are, where did this technology go and what did it influence? So we're coming to the last phase of my slides. I'm sorry they're taking a long time. I don't know if anybody's gone to sleep. For this, we're going to look further afield, beyond Sri Lanka. We're going to look at Burma, Cambodia, Sarawak, and ultimately to Japan. And these are all sources of evidence that were in existence. I haven't been to see these places. I'm working off known material, but making connections. And we're going to start in Burma with sites that were near Pagan and investigated by Bob Hudson from Sydney University. Furnaces that he says produced iron and steel, or not, he says, we know produce iron and steel. They date from the 11th to 13th century. They're possibly earlier. He talks about side walls tapering outwards towards the bottom, forming a long, narrow base. Well, these same furnaces were actually described as early as 1864 in a very famous series of books called Percy's Metallurgy, in which he describes the natural draft furnaces of Burma. These are not wind-driven furnaces. These furnaces use the height of the chimney to draw air through. But what's important here is that the base of this furnace is a long, narrow slot. And in his description, Percy says it's 5 foot at the bottom, while the depth from front to back is 1 foot. And into this opening at the bottom of the furnace is said to be closed with moist clay, into which 20 small clay tubes or tuyeres are built. So if we translate those measurements into a schematic footprint in the way that we've been using so far, this is what we get at the base of this furnace. So that looks familiar. Now let's move to Cambodia, to an account which is known from ethnography. Again, it claims to be making iron and steel. We know it operated in the 19th century. It could well be earlier. And in this description, it says it's a long rectangular in plan, 0.9 of a meter wide and 2.5 meters long. Each side has 26 holes with 26 tuyeres, and project some distance into the furnace. All tuyeres on each side are connected by bamboo tubes to a common bellows. So this is neither a wind furnace nor a natural draft chimney furnace, but this is a bellows furnace. But if we again use those same measurements to create the footprint, this is the image we get. Again, it's looking familiar. If we now go to some evidence from Sarawak, we have here not a furnace, but we have descriptions of slag morphologies. And I'm not going to read it all out, but essentially what they're describing is this same slag morphology that we see for our telescope tuyeres. Tuyeres captured inside these cylinders. They don't fully understand it, but they have described this. So something very reminiscent of our technology in Sri Lanka. Finally, we move to Japan, where we know we have very famous steel making in furnaces called Tatara furnaces. But when we look closely at this Tutara furnace, which is often regarded very much as a technological outlier, you know, it's an unusual, and again, the term unique has been used for the Tutara steel making furnaces of Japan. But let's look a little bit more closely. Again, this is a bellows driven furnace, driven by manual bellows, a rectangular structure with multiple tuyeres in the long sides of the furnace. We know it makes steel, we know it makes iron. If we use our same approach to create the schematic plan, this is what we get. And then we can play around using exactly this to the same scale. This is our largest Salmonella lever furnace. And if we take another one and we turn it around, because we don't need to use the wind now, we're using bellows, connect them up, we have a structure which is very, very close to the Tutara furnace. We know that the Tutara furnace produces iron and steel, and it dates from the earliest date from about the 6th century. So our bits of evidence, for me, suggest that we have an Asian technological tradition of steel smelting, direct steel smelting in rectangular or linear furnaces with multiple tuyeres. The earliest of these is our evidence from Sri Lanka, and all of these fall later. The only one which is wind powered is our furnace in Sri Lanka, our hilltop furnaces in Sri Lanka. So we're not talking about a tradition of using wind power. We're talking about a tradition of direct smelting to steel in a different furnace geometry. So as far as I'm concerned, we could not, and we cannot and should not use the word unique. And that's my message today. It's not unique. It's a major contribution to the history of non-Western technology. And I think I finally got to the end. Apologies for the length of time it's taken. Thank you. Back with you. Am I? Is anybody remaining? Anybody left?
Yeah, no, we are still there. It was a very nice presentation, Gail. Yeah, I think first of all, it was an excellent presentation with a lot of information, but I want to thank you for taking Sri Lankan heritage to global community. Thank you very much. We really appreciate your commitment and your commitment to this field, right? So now this forum is open for some questions and discussions. That there is a comment from Vidura, the lecture is the best I attended in a long time, right? I also endorse it, right? So questions and discussion time, right? You can raise your points or the questions in the chat box.
I would be very happy to see people, because you're all looking at me. I would be very happy to see if people were willing to turn on their cameras.
Yes. Yeah.
That would be very nice for me.
Yes. Yes. Shall we just switch on our cameras for a minute, right? So then Gil would be very happy to see the audience actually, if possible, right? So we know that I also have a power failure at this moment, right? So yeah. That is, you know the situation.
I know the situation, but I can see
any questions from the audience that that everybody is appreciating your presentation. It was marvelous actually.
Udeni, the switching on camcorder is not allowed by the admins. So
yeah.
Okay. Right. So maybe ISL is handling that part, right? Yeah.
I'm Lalindra. May I ask a question?
Yes, please. Yes.
Gil, it's very interesting and very nice presentation. My question is, now direct smelting to steel, does it also depend on the material used?
Sorry, does it depend on the what?
The material used, the raw material used.
The raw material.
Yes.
all smelting, successful smelting does depend on the raw materials you use. You know, you need the best ore that you can access. That doesn't necessarily mean the highest iron content. It means the right combination of iron with the other minerals that you use to make the slag. The fuel, you need a fuel which is efficient. You need a structure, an apparatus that is resistant to temperatures and is designed to give you the highest temperatures and the most efficient temperatures. So it does it depends very much on all of those things. They all need to come together for you to be able to successfully smelt iron, but also then to be able to take it to making steel. How can I explain that a bit further?
Yeah, I got it, Gail.
You got it. Okay.
That means whatever the carbon content in the original material, you mean that the efficient smelting will give to look the high carbon steel, right?
The carbon that we get into the iron to make the steel really is comes from the operation of the furnace. It comes from the burning of the charcoal fuel, but you have to burn it in such a way that the reactions take place in a way that allows some of the carbon to absorb into the steel, into the metal to create the steel. So it's, I mean, it's right at the edge of my knowledge, but it is to do with both the materials and also the design and operation of the furnace.
May I ask a question?
Right, thanks.
Yeah,
Is it
Dr.
possible
Dev
to
Surendra,
get
please.
Yeah.
Dr. Udeni, shall I
Sorry.
answer the question?
Well, I can't turn on my, yeah, so you can see me if you want to. Well, it's dark here because we are under power cut.
Oh,
Yeah, I'm missing a hotspot, right? I'm missing a hotspot, right? Using my cell phone. Now, the thing is, now the question is this: what are the last, the latest evidence of this kind of steel being made in the country that you have found? You know, say now it was, well, you have found kind of in 400 BC up
Yeah.
to about 800 AD. Now, what's the earliest, I mean, the latest time at which they have been producing this kind of steel in the country, according to your findings?
okay. That's addressing that question is complex, because there is two things we should be clear about. Knowing that steel is being made depends on us being able to analyze artifacts and objects. What we have demonstrated is that the furnaces that we're looking at are capable of making steel, and that we have made steel. Yeah. So to be able to confirm that steel was being made, you couldn't not make it in our furnaces, but that's another question. We need to start analyzing artifacts. That means we really need to take samples and look at them microstructurally. That hasn't been done. There's a fantastic piece of research in that to be done. Now, having said that, so that's one part of the answer. The second part is, we know that our furnaces were capable of making steel. We know that our furnaces on the hilltops at Samanillaveva disappeared from the archaeological record in about the 11th, 12th century. That's another set of... However, we also know, and this is another lecture, if you invite me back, is that we could make steel using crucibles by refining iron in crucibles. And this is the whole story of wood steel. And that's part of what was described by Ananda Kumar Swami in medieval Sinhalese art, and we know it from India. So there are other processes by which you can make steel, not necessarily direct smelting, but by refining. And so that steel would have gone on being used. Does that help? Does that answer some of what you're asking?
Yes.
Okay,
Right.
fine.
Very much, yeah.
Gil, there is a question actually. What are the reasons for abandoning this marvelous industry in Sri Lanka? That one question came from Nihal Puri.
Well, sorry, say that question again.
Yeah. What were the reasons actually for abandoning all this? That we somehow we lost this technology.
Yeah.
Right? Have you found some reasons for that?
Well, that's a really very good and very interesting question. I can't give you a direct answer from direct archaeological evidence, but what I can do is to give you my intuition, which is based on what we all know is history of the island. So we have this evidence, very strong, very clear, going right up into the 11th, 12th century at Salmonella. Then it disappears from the record completely and unequivocally. It doesn't subside. It doesn't translate into a new technology. It simply disappears. That is very interesting that it does that. My interpretations on this are that these furnaces were making very high carbon steel, and that steel was being exported out of the Salmonella area to the coast to be exported out of the island to the Middle East for weapons making. The problem with this high carbon steel is it's not a steel that you can easily forge in a blacksmith's forge. It can only be forged, or it takes a specialist smith to forge that steel. So your normal blacksmith in the village in Sri Lanka is not going to welcome this material. They would far rather have a lower carbon steel or wrought iron that they can make agricultural tools and domestic tools from. So you're making steel for a market, for an external market, a different market. So you would depend on merchants, intermediaries, middlemen coming seasonally to the area to take your product to the coast or to wherever it is. This is conjecture. I don't have the direct archaeological evidence for this, but it makes sense to me. What happens in the 11th, 12th century in Sri Lanka? There's a huge demographic upheaval and political upheaval with the incursions from South India. And the whole stability of the country is turned on its head. Which means that those connections across country, those middlemen, that whole system possibly is breaking down. If your intermediaries don't come to collect your product, you're not going to make it. You're not going to go back up on those hills and make that steel again if nobody comes to take it from you. If those intermediaries are, in a sense, licensed by a central authority and have the authority to go and trade, if that central authority is disrupted or changed, those intermediaries maybe lose their license to do that work or lose their authority to do that work. So that's how I interpret the disappearance of this technology. There is a lot of research that can be done to try to tease out whether that actually is the case. And I would love to see someone take that on as a research project. Because it would be It would, so it means the technology is dependent on the political infrastructure. Does that answer the question?
Sorry, can I ask a question there, please? Can I ask a simple question there again?
Yes.
You got a little bit of high carbon steel out of your furnace. You showed us the thing that you extracted out of the slag. Did you manage to get it forged into a little bit of a bar of steel? Because you got your iron kind of you got it forged into a bar, right? I mean, did you manage to get it done by the local blacksmiths?
No.
The little bit of hard, the high carbon steel that you got. Yeah.
The simple answer to that is no, we didn't. The first piece of low carbon iron, the blacksmiths were able to forge very easily, and in the end they liked it. That high carbon material was very much embedded in the slag. So we weren't able to separate it. And to be perfectly honest, it felt like important material that we should not do that to. We didn't have it in sufficient quantity to play around with. It would certainly be an interesting thing to try to do, but we weren't able to do it.
Why do I ask this now? Because perhaps if there was sufficient quantity, they would have even tried it. Maybe it's not for the lack of capability. Maybe it was for the lack of inexperience in the present day's context, right?
Yes, absolutely. I mean, yes, it's you know, the blacksmith could probably deal with it, but it's not the same as dealing with the normal low carbon iron. They would have to
did in the past, right?
Yeah, absolutely. Okay.
Thank you very much.
Mr. Sarath Seneviratna, yes, please.
Yes, thank you. And well, it is not a question actually. It's going to be a comment. I saw you and your team at Peradeniya many years ago at the initial stages of your research work when you made a presentation there at Peradeniya. And well, I mean, it was amazing even at that time. But the things that you have done after that is very, very impressive, I would say. And I think you have done a marvelous job in extending the work that we saw many years ago. And thank you very much for doing all that.
Thank you, really. Thank you so much for your comment. I remember giving that lecture in Peradeniya, and it was a very exciting time to do it. I do remember, and I've always really enjoyed I enjoy presenting this work. And I do think that the work that we've done since has been very much to do with interpretation and exploring the meaning of all of this. There's so much more that could be done in the field, so much more that could be done in the laboratory. I really would love to see people take up this research. There's still so much to be brought from it. Thank you.
Excuse me, madam. Can I ask something?
Go ahead.
Shall we go by the order, right? So,
all
Kavan,
right, whichever.
Yes.
Okay.
Kavan, yeah.
Been identification of the steel found with Damascus steel. I just want to find out what the evidence of identification. You also talked about it being exported to the Middle East. I want to find out about the evidence for that, to identify it. Some analysis of the impurities or something to tell us that this is the steel that came from Sri Lanka.
Again, that's a difficult one to give you very direct evidence for. The thing with high carbon steel, the distinctive thing here is that steel that we made in our furnace had been molten. It had been liquid, which means it's created at very high temperatures. With a liquid steel, you get a very thorough mixing. All the impurities in it float off or float away. So you get a very homogeneous, well-mixed, impurity-free steel. That is, and you can see that in its microstructure. And that's what we could see in the microstructure of the steel that we made in our furnace. That is the microstructure that you see in any of the ingots of steel that come from crucibles, as in the sorts of crucibles that Ananda Kumar Swami had described. And that is the same, it's this slag-free, homogeneous, high carbon steel. And that is the same material that then eventually gets used in swords. Let's just call it swords. But of course, by the time it's gone from the condition that we saw it in, which is as, let's just say, in its, I was going to say raw, but I don't like the term raw, in its manufacture, no, I've got to find the right word. The process of turning it into a sword changes its structure. So you do not see exactly the same structure because it's been forged, it's been hammered, but you see in a sword that it is slag-free and it is this high carbon steel. Am I making some sense? Yes. Again, I come back to
Pushparaja, please.
Yeah, thank you.
Just to add to, hang on, just to add to that, I come back to the fact that we haven't done enough analysis of objects to be able to give a clear evidence trail from the material coming from furnaces to the material that's ending up in objects. Yeah, sorry. Okay, carry on.
Yeah, thank you. Actually, a very good presentation. We enjoyed a lot. And Dr. Gill, I had a question. All days, from this smelting process, there were some impurities, maybe. So from the ore and alloys and other things, maybe mixed. What are the technologies used to separate the steel, the separations? So is there any technologies used, or else they use the same as it is?
The first impurity you have in the metal when it's melted is the slag, the material you don't want. Yeah, so the more efficient you can smelt, the more liquid you can make your slag, then the more it's going to flow away from your metal. One of the things that a furnace has to do is has to separate the metal from the slag. We were only partially successful in doing that. You know, the fact that we've got metal and slag stuck to each other is not good. In terms of smaller scale impurities, generally, you can't extract them. They remain in the metal. Yeah, they remain as part of the metal. Yes. You may have phosphorus, you may have other bits and pieces. Some of them will strengthen the metal. Some of them will not be so beneficial. But the main impurity is to take out the slag. If you imagine the slag to be like soup, and it's like a soup in which you put all the things you don't want. And in a furnace, yeah, in the furnace, the soup becomes liquid before the metal. The slag becomes liquid. The metal still remains solid. So the slag will flow away. Yeah? Does that make sense?
Thank you. Thank you.
Okay, thank you.
Yeah, I think There is another one from Dr. Devasurind. I think Dr. Gill has been talking for now 1 hour and 40 minutes, right?
I'm happy. I'm happy.
Okay.
If I wanted to just make this comment, I think it relates to the question that have been posed by the previous speaker. Now, see, if you can put the molten steel into a ladle, the problem is sorted out, because your slag will float and you can remove it the way they remove the slag. I mean, just put all kinds of chemicals nowadays. I think Dr. Jill will agree, because if you go into any foundry, that's what you will see. But my question is, now they were not, they wouldn't have, well, the way you did it, it was not possible to take the molten steel into a crucible or into a ladle, because the way that we do it normally, because you take it in a ladle and then you pour it into a mold, right? Now, to the way that you did it, you just broke the front wall and the whole thing pours out, right? I mean, it flows out. Now, maybe that's not the way they did it. Maybe they took it out into some kind of a ladle. Wouldn't you agree, Dr. J?
Well, it's possible. What I would say here is that if you imagine being at that furnace and it's operating, I've now done it 5 or 6 times, but I am absolutely not an iron smelter. In the past, there would have been experienced smelters who ran those furnaces, who knew how to operate them. And there is an enormous amount of knowledge and know-how about how you operated them. For example, how long you smelted, when and how you broke the wall down, how you extracted the metal. Did you do anything before you extracted the metal? Did you add anything? Did you let the charcoal burn down? These are all the real subtleties of a master smelter.
I will just add a word,
that are very difficult for us to get to. And
long time back, I read this, the novel Rape of the Fair Country, of the you'd have read it, right?
Yeah.
About the Welsh steel industry and so on, where the thing will blow into the face of fellows and so on, right? Now, so this is known. Perhaps our people, those people who are doing it, they knew it. But when the thing gets forgotten, the whole thing gets forgotten with that too, because as you said, economically, it was not feasible for them to do it. I mean, you explained it very clearly, right? Perhaps we will never find it.
Yeah.
Very much. Yeah. Thank you very much.
Yeah. Yes. Can I? I just.
There is one question.
I just wanted to say that I can see many comments in the chat, and I'm not going to have time to address all of them at the moment, but I'm thankful to everybody for the many comments they put there. Sorry, there was another question.
Gil, shall we take this last question from Dr. Bohingam? Can you please raise your voice, Dr. Bohingam?
Hello, Jill. Nice to see you, and thank you so much for your excellent lecture. Now, this is for an opinion from you. You said that probably the decline of Samanalawewa steel industry might be linked to the South Indian invasions, preventing the Middle Eastern buyers coming to Sri Lanka. I mean, it was kind of a possibility that you mentioned. What I would like to hear from you is about the other archaeological material that we find in Sri Lanka in places such as Manthai and so on, datable to say 10th, 11th, and even 13th century, like ceramics. there are clearly datable ceramics, which various people have sort of identified to be made in Middle Eastern areas, datable to say 11th, 12th, 13th centuries. So they were coming in quantitatively at places like Mantai. They were, quantitatively larger than those were coming from China. So how will you explain that scenario? Thank you.
Well, I understand what you're saying, Bohin, and nice to hear from you. I think I would not suggest necessarily that there was no trade with the Middle East. That's not what I'm suggesting at all. I'm simply suggesting that the political change in the country would have disrupted certain networks, could have disrupted certain networks. And if you are in the heart of Samanileveva, and dependent on somebody who would seasonally come across the plains, up the hills and over the Kaltoto escarpment, who for whatever reason, it didn't work in that way any longer, you would very quickly lose your incentive to make that material. I'm not suggesting for a moment that the incursions from South India disrupted all contact with the Middle East. I don't think that's the case. You're absolutely right. Yeah. There's plenty enough other evidence. I think one of the other things in that discussion is that period in the 11th, 12th century also is a period when we begin to see the emergence of steel making in crucibles in South India. So it's possible that not only do you have a disruption, a political disruption within Sri Lanka that leaves these peripheral people, these marginal communities in Samanileveva marginalized, but also you have an alternative market source emerging in South India. So your traders who may just say, oh, it's really difficult to get to Samanileveva now for whatever reason, they may say, okay, well, we can find steel in South India. So it may be that that's another element to what happened.
Yeah, thank you very much.
Okay.
Yeah, with that question, I think we are going to the end of this session. We already, I think everybody has acknowledged and appreciated your presentation, but formally to propose the vote of thanks, I would like to invite Dr. Samanthi Senaviratna, the secretary of this History and Heritage Forum. Dr. Samanthi, over to you.
Can I just make one comment before that?
Dr. Samanthi, yes.
Can I just make one comment before that? Because you are...
Yes, before that. Yes, Gil. Yes, Gil.
You are a community of engineers, which I think is really exciting. I know that amongst you there are people who are taking forward the study of how these furnaces work in terms of the air, the fluid dynamics. What I would love to see and hear about is some of engineers taking forward some of this to look at what could be done with some of these furnaces, not for making iron or steel, but for using that power of the wind to look at the topography of those hills and the power of the wind, and to see what alternative innovations can come from that. So I'd love to hear somebody taking that
Thank
up.
you, Gil.
Okay.
Yeah, thank you very much.
Sorry,
for the suggestion. Yes.
So enough time for me to be quiet.
Sorry, just a quick question.
Good day, everyone.
The windmills, the wind-powered mills, would you consider those?
The wind-powered?
The modern technology of the wind-powered winds in Samanileveva.
Yes, I'd love to see it. What we've learned is about the velocity of the wind and what it can do when it reaches the top of those hills. And if you design a structure carefully, how you can accelerate that wind on the crest of the hill I'd love to see that taken forward.
Okay, good evening, everyone. First of all, I would like to thank Engineer Dr. Kamal Laksiri, President-elect of the IESL, for initiating this event as the first event of the History and Heritage Forum. And thanks for his continuous effort, we were able to listen to this truly fascinating webinar. I extend my gratitude to our presenter, Dr. Gil Julef, joining from University of Exeter, for taking time out of her busy schedule to grace this event. Actually, her research work, especially her untiring enthusiasm in exploring ancient engineering heritage in Sri Lanka, it is very interesting, and I am sure this evening was an truly fascinating and eye-opening experience for all of us as engineers. So I must thank the organizing committee, including Professor Udeni Nawagamuwa, President of the History and Heritage Forum, and our engineer Chanaka Priyantha, who prepared the flyer for us, engineer Kamala Gunawardana, and all the IESL staff members for working hard to make this event a successful webinar. Also, I would like to thank the huge audience we got for this very first event of the History and Heritage Forum. We had nearly 130 members, a multidisciplinary audience. Thank you very much for joining with us this evening. And this is the first event of this forum. And in future, we are planning to organize many more events. I invite all of you to join with us future events as well. Thank you very much.
So shall we just say thank you? Thank you.
Thank you. Yeah.
Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you. Thank you.
Thank you. Thank you.
Dr. Kamal, do you have
Thank
to
you.
say anything? That is over now.
No, Professor Udeni, thanks.
Yeah, Dr. Kamal, yes.
Thanks. Thank you, Jill, conducting this interesting lecture, accepting our invitation. It was very nice, and in fact, I was fortunate to attend your field trials in 2007. So that's why I decided to propose Professor Udeni to conduct this lecture. Most of our members will like it. So you did a very good job. So let's listen again some other topic later.
Thank you very much. It's been my pleasure to talk to all of you. It's really nice. It's been worth it. Yeah. Thank you.
Okay.
Bye. I'll read through all. I'm going to read through all the comments
Yeah,
before
thank
I.
you.
Yeah.
Yeah. Shall we wind up the session, and then thank you very much for joining, and it's good night from Sri Lanka again. Right, it's almost 7 p.m. in Sri Lanka, right? So
Good night. Thank
I'll
you
close
very
the
much.
meeting. Thank you.
Thank you very much.
Yes.
Bye.
Thank you. Bye-bye.